Okay, today's talk will be mathematical nonsense as used by Einstein's relativity. And Einstein's relativity can have all its mathematical nonsense sorted out properly, but the people who actually use Einstein's relativity seem to prefer to use mathematical nonsense. So this is a part of Einstein's relativity as by those people. And I will be dealing with the video Special Relativity A-level Physics, and it's at that internet site. So if we go to it, it's there. If I can start it back at the beginning, it's there. A-level Physics revision. Go back. Right. Right. First thing I need to do is to explain some maths, and I'm going to be using this Wikipedia site for some maths, and then I will show you a little video on this maths, and then I'll get back to the physics place where their maths is used. Right, so let's start. No, it's not it. Wikipedia is here. This is from Wikipedia. Mathematical fallacy. Wikipedia. In mathematics, certain kinds of mistaken proof are often exhibited and sometimes collected as illustrations of a concept of mathematical fallacy. There is a distinction between a simple maths mistake and a mathematical fallacy in a proof. A mistake in a proof leads to an invalid proof just in the same way, but in the best known examples of mathematical fallacies there is some concealment in the presentation of the proof. For example, the reason fidelity fails may be a division by zero that is hidden by algebraic notation. There is a striking quality of the mathematical fallacy as typically presented. It leads not only to an observed result, but does so in a crafty or clever way. And what I will be dealing with in Einstein's relativity is the problem of division by zero. And if we go down a bit, we have Wikipedia goes into the explanation of division by zero fallacy, and it gives an example. This is an example of using division by zero to show that 2 equals 1. And of course, when you find out 2 equals 1 by a bit of algebraic manipulation, that is a mistake. So first step is to say, let A and B be equal non-zero quantities. A equals B. Next step is to multiply by A. So you multiply A times A, get A squared. Multiply B by A, get AB. Next step is to subtract B squared from both sides. Subtract B squared from there and B squared from there. So you then get that equation. And then next step is to factor both sides. And you factor in that both sides. That side is that. A times A squared. Minus B times A, and then add that to A times B, so that equals 0. Those two things come 0, and then in the final one, minus B times B gives you minus B squared. So that is factored. That is that. And on this side, you bring out the B. So B's brought out of the brackets. B times A is that bit. B times minus B, B squared minus B squared there. Right. Now after you've got that equation, you then divide both sides by A minus B. So when you do that, divide that by a minus b, gets rid of that from that side as well. So that you left on this side is a plus b, on this side is b, so you've got a plus b equals b. And then you observe from the beginning that a equals b. So putting a equals b equal to that, it's a equals b, b plus b equals b, combine, so 2b equals b, divide both sides by b, and you have 2 equals 1, which is nonsense basically. And the problem is that when you divided by a minus b, that was 0. A equals b, so a minus b equals 0. So dividing by a minus b, you were dividing by 0. You have to be clever with maths and recognise you can't do that. I have a little video here that will go into it again in more as to what I've just done.
Today we're going to prove that 1 equals 2. This is certainly not mathematically correct, and our job is to determine where the problem is in this proof. What we say is that there's a fallacy in the proof. We're going to go through each step, and then you can go back and determine why the proof is invalid. In our first step, we're going to let A equal B. So A and B are equal to each other. We're going to multiply the left side by A and the right side by A. As a result of this multiplication, we have A squared on the left side and AB on the right side. We have A squared equals AB. I'm going to subtract B squared from the left side and B squared from the right side. Both sides are factorable. Here we have the difference of two perfect squares. The factors, A plus B, A minus B. On the right side, we have a common factor of B. If you factor out the B, the other factor is A minus B. We have two factors on the left side, A plus B, A minus B, and on the right side, B and A minus B. We'll divide the left side by A minus B and the right side by A minus B. This is a common factor on the left side, so these two terms go out, and similarly, those two terms on the right side go out. We're left with A plus B equals B. A plus B equals B. Since A equals B, I can make the substitution, and I get B plus B equals B. 1B plus 1B is 2B. So on the left side of the equation, I have 2B, and on the right side, B. If I divide each side by B, I get 2 equals 1. Since we have 2 equals 1, these sides can be interchanged, and that means that 1 equals 2. Something is very wrong. Can you find the fallacy?
So the fallacy is A minus B is 0. A equals B, so A minus B is 0. And so what you've done here is divide by 0. And Einstein's believers in Einstein like to use that sort of maths, as you will now discover. Let's go back to my link here. Now on to the video, Special Relativity A-Level Physics. Yeah, right, it's at that link. It is typical of the type of maths presented for Einstein's relativity. The maths will be slowly built up. There is a great deal in the maths that does not make much sense, but I will be concentrating on when they apply the mathematical fallacy of division by zero. So dividing by zero is what we're going to look out for. It's going to take a long time before they get to that, but they will get to it. Here we go. Let's have the sound up a bit more.
Hello, today we're continuing in our A-Level Physics Revision series looking at the subject of special relativity. You can find more advanced videos on this subject in my playlist on special and general relativity. Special relativity applies to inertial reference frames, which essentially means non-accelerating frames. That is to say that in special relativity people are either stationary or they're moving at constant velocity. And relativity means that you and I have different relative perspectives on the same event. Let's suppose that you and I are in boxes. Here am I, this is me, and this is you. And all we can do is to see each other through a little peephole. We have no means of seeing anything else that might serve as a reference point. What we can see is that we're travelling away from each other. So this distance is getting larger. I might think that I am stationary and you are moving away with a certain velocity v to the right. You might think that you are stationary and I am moving away with a certain velocity to the left. Or it could be that we are both moving away from one another with a combined relative velocity of v. But here's the thing. There is nothing you can do, no experiment that you can perform, that can establish whether one of us is stationary and the other is moving away, or maybe that both of us are moving away. All the laws of physics will behave in exactly the same way if we are stationary or if we are moving at constant speed. If you are juggling, if you are playing snooker, all of those things will work just as well in a moving frame at constant velocity as they do in a stationary frame. That is not true in an accelerating frame. If one of these is accelerating and you try to juggle, the balls will fall because they won't land in your hand as you expect them to do so. Now the special relativity...
Right, I think I should emphasise that up to now that was just Newtonian physics. It's relativity within the context of Newtonian physics. He's going to now say something which is supposed to be special relativity.
As we understand it today, all derives from an experiment performed by two people called Michelson and Morley. And they were trying to find the...
Right, I have dealt with Michelson-Morley in a previous video. It's this one. If I enlarge it. The lie on which Einstein's relativity is built. They're making what they are doing in relativity, the people who believe it, is they're making false claims about experiments like the Michelson-Morley experiment, and I have dealt with it in this video here. So I will keep reminding you for a while that what he's saying about the Michelson-Morley experiment is wrong, but he's trying to use the Michelson-Morley experiment as justification for what he claims about special relativity.
Speed of Earth through space, they called it the ether. The speed of Earth through the ether. They knew that the Earth went round the Sun. They knew that the Sun went round the galaxy. But the real question was, how did Earth move relative to space itself? And they based their experiment on this principle. if you take a river that is flowing at, let's say, 3 miles an hour, and you have a rower who can row in...
Right, I think I should point out, like, after all that stuff about the Michelson-Morley experiment, which I would not agree with, and it's falsely representing the Michelson-Morley experiment, he now is back to Newtonian physics. He's considering the case of a river, and he's doing the maths within the context of Newtonian physics. So we're back to Newtonian physics for now.
How did Earth move relative to space itself? And they base their experiment on this principle. If you take a river that is flowing at, let's say, 3 miles an hour, and you have a rower who can row in ordinary still water at, let's say, 5 miles an hour, and you say to that rower, I want you to row across the river and then come back again, and we will time you, then the rower, of course, will not row across, because if he does, the river will carry him downstream. So the rower has to row in that direction at 5 miles an hour, and the river will push him so that, in fact, his actual transit across the river is in that direction. The river is flowing at 3 miles an hour, he's flowing in this direction, he's travelling at 5 miles an hour in that direction. We all know that the 3, 4, 5 triangle, or you can use Pythagoras to show that the actual speed across the river will be 4 miles an hour. And that will be true when he comes back as well. So if the river is 1 mile wide, then the rower will have to row across and back, that's a total of 2 miles, at 4 miles an hour. The total time to cross and come back will be half an hour. Now let's say the rower, we want you to row 1 mile, that is the same as the width of the river, 1 mile downstream, and then we want you to row back again. Well, when the rower is rowing downstream at 5 miles an hour, the river will also carry him at a further 3 miles an hour because the river is flowing. So he'll go downstream at 8 miles an hour. And that mile will take him 1/8 of an hour. But when he rows back at 5 miles an hour, he's rowing against a river which is flowing at 3 miles an hour. So his net progress will be only 2 miles an hour. And therefore the mile that he has to travel to get back will take him half an hour. And that means that the total time to travel there and back will be 5/8 of an hour. And the critical thing is that that is different from the half an hour it took to row across the river and back. So in other words, even though in still water the rower travels at 5 miles an hour, when he's going across the river and back it takes half an hour, but when he goes the same distance downstream and back it takes 5/8 of an hour.
And that is still Newtonian physics. So, Newtonian physics so far.
When he's going across the river and back, it takes half an hour, but when he goes the same distance downstream and back, it takes 5/8 of an hour. Now, if I hadn't told you that the river was travelling at 3 miles an hour, but I had given you all the rest of this information, you could have calculated that the river was flowing at 3 miles an hour. And Michelson and Morley took that self-same principle, and what they said was, if we can do a same kind of idea of getting something to travel across and back and down and back, and measure the difference in the time it takes, then essentially we can measure the flow of the Earth through space, because that's essentially the equivalent of the river. Instead of using a rower, Michelson and Morley used light. What they did is they took one light beam and they took it to a mirror that was a beam splitter essentially. It's half silvered and half allows light through. So some of the light was reflected up to a mirror up here, and some of the light went through the mirror and to a mirror here. And these distances are about the same. You can't make them exactly the same, but about the same. And then, of course, the light would be reflected from the mirror and come back again, where it would hit this half-silvered mirror, and some of it would go straight through, this beam would be reflected, and that would come down to an eyepiece. So you've got light that is reflected that way or goes through the mirror that way, and when the light beams come back, they recombine at this mirror and come down to an eyepiece. Now, because you've got a single beam of light that's been split and then rejoins, you're going to have an interference pattern, which basically means you're going to see a series of fringes. And those fringes will be light, dark, caused by interference. It's the same principle as ripples on a pool interfering with another set of ripples. You can see this in my video on waves. But here's the important thing. If you now move or rotate this whole experiment, take the whole thing and rotate it, then it's a bit like the rower, instead of rowing 1 mile in that direction, rowing 1 mile in that direction, or 1 mile in that direction, or 1 mile in that direction, or 1 mile in that direction. And as we've seen, the time taken for each of those would be a little bit different because of the effect of the river. So the idea is that if the Earth is travelling through space at a certain speed, then if you rotate this experiment, then the time taken for the light to travel to the mirror and back will be slightly different. And consequently, the interference pattern will be different. So as you rotate the experiment, these fringes will move. And measuring the extent of the movement of the fringes will enable you to calculate what the speed of the Earth is through the ether. So Michelson and Morley did this experiment, but the trouble was, every time they moved the equipment, the fringes didn't change. And that suggested that the amount of time it was taking for the light to travel there and back, didn't vary according to the rotation of the equipment. That's
right, and that is false, as pointed out in my video here. False claims are being made about the Michelson-Morley experiment. So back to this.
Didn't change. And that suggested that the amount of time it was taking for the light to travel there and back, didn't vary according to the rotation of the equipment. That's rather like saying that the time it takes for the rower to go up and down or side to side is exactly the same.
False claim.
But we showed that it wasn't and couldn't be if the river is travelling. Experiment, that the Earth isn't travelling through space at all, it is stationary. But that's not a very likely outcome, since the Earth we know goes around the Sun, we know the Sun goes around the galaxy, so it's impossible for...
Yeah, well anyway, all that is just false claims about the Michelson-Morley experiment. They're deducing the result based on false claims.
The Earth to be stationary in space. The other conclusion that you'd have to come to, therefore, is that the time it takes for the light to travel this distance is irrespective of any movement by the Earth through the ether. That is to say, that the speed of light, c, is constant, independent of the speed of the observer or the speed of the source.
False claim. So they're using the Michelson-Morley experiment to try to back up their false claim. So there you go.
And that turns out to be a critical point when it comes to special relativity. Why is that? Well, let's consider you on a train.
So we're now having to look at the consequences of this being a constant value. the light speed in vacuum being a constant value. So putting aside the issue that the experiment didn't really show that, we are now going into the maths based upon that belief. First of all, I think he's going to look at Newtonian physics based upon this belief. So, picking it up.
There you are. And the train is travelling at this direction at 30 miles an hour. And you have a small ball which you roll along the corridor of the train in the direction that the train is moving at 10 miles an hour. What does an observer, that's me, standing on the platform, observe as the train goes by? I see a ball on the train travelling at 10 miles an hour, but the train itself is travelling at 30 miles an hour. So I will observe that the speed of the ball is 10 plus 30 equals 40 miles an hour, relative to me.
That is Newtonian physics. Newtonian physics addition of velocities. Go back a bit and pick up again.
Observe as the train goes by. I see a ball on the train travelling at 10 miles an hour, but the train itself is travelling at 30 miles an hour. So I will observe that the speed of the ball is 10 plus 30 equals 40 miles an hour, relative to me. It travels at 10 miles an hour relative to you, but because the train itself is travelling at 30 miles an hour, I say that the ball's total speed is 40 miles an hour relative to me. Now let's do exactly the self-same experiment. Here are you on the train, which is travelling at 30 miles an hour, and instead of having a ball, you shine a torch. And the speed of the light that comes out of that torch will be c. I am standing on the platform, and I measure the speed of that light. Now you would think that the light should be c, the speed on the train, plus 30, the speed of the train, in exactly the same way as we had up here. But
that is Newtonian physics. Still Newtonian physics. Just pick it up another bit here. Back again a little bit, and on again.
Light. Now you would think that the light should be c, the speed on the train, plus 30, the speed of the train, in exactly the same way as we had up here. But that would be wrong, because according to Michelson and Morley...
And he's wrong. He's wrong. He's putting a cross on there, and that is wrong. And he's citing the Michelson-Morley experiment for putting that cross on there. And he's got the Michelson-Morley experiment wrong. So picking up again.
Plus 30, the
Which
speed
is correct.
of the train, in exactly the same way as we had up here. But that would be wrong.
And there should be a
according
tick.
to Michelson
That's
and
wrong.
Morley, what I will measure is that the speed of the light is c. The same speed that you measure, irrespective of
That
the
is wrong.
speed of the train. And as we shall see, that has some rather intriguing consequences. So let's see why. Let's imagine that I am once again the observer.
So at the moment we're having to go along with his claim that it's C instead of what it should be. We're doing the maths based on it being C.
This is me. And I have marked out my frame of reference. That is to say, I've effectively put meter sticks along the ground, and I've marked off every meter right the way along the ground, and that's my measuring scale. You are travelling, if you like, on a train. Here are you, and you've got your own measuring system on your train. Along the corridor of the train, you've marked off meter elements. And the train is travelling at a speed v. This is you, this is me. And just to distinguish any measurements we may make, I'm going to say that all the measurements in your time frame measurements of distance will be x prime, and measurements of time will be t prime, whereas in my frame, measurements of distance will just be x, and measurements of time will be t. So wherever we put a prime, that's what you measure. Wherever we don't put a prime, that's what I measure. And I can draw a space-time diagram that is simply time here, space here. I'm using x and t because those are my measurements. And I can plot your velocity. That will be a straight line because you're going at constant velocity. Special relativity requires that. You're going at constant velocity, and I can measure that velocity. It's simply the distance you travel, x, divided by the time you take to do it, t. And that is the line of your velocity. I could incidentally also measure the speed of light. That will be c. By convention, we tend to draw the speed of light at an angle of 45 degrees. But the point about this is that the scale has to be such that this is the speed of light. So, for example, if this is 1 second, then this has to be 3 times 10 to the 8th meters, because light travels at 3 times 10 to the 8th meters per second. Now, how do I calculate how far you have travelled? Well, here we are. This is me on my graduated scale. And here is you travelling at speed v in this direction. And I will say that you have travelled this distance, which is x, measured on my scale, in time t. And that means that your velocity is simply the distance you've travelled divided by the time. V is x over t, or if you like, x equals vt. By contrast, you are standing on your scale, and you are saying, compared to my scale, compared to the scale that's on your train, you're not moving at all, because you and the scale are both moving at v. So compared to the scale, you are not moving. So you say that in your frame of reference, x prime, which is the measure in your frame of reference, is 0. That is to say, you are not moving with respect to your frame of reference, because both you and the frame of reference are on the train. So the frame of reference and you remain in the same place relatively.
Okay. Now, I think it's important that he's saying that x prime is equal to 0. Make a note of it. Does it come out clearly? X prime equals 0. That's what he's giving. I mean, that's going to be useful to us in a minute. Picking up back again.
And the frame of reference are on the train. So the frame of reference and you remain in the same place relatively. So you say, you're not moving. I say, you are. Now then, if x equals vt, then x minus vt equals 0. But x prime equals 0. And so we get that x prime is equal to x minus vt. All we're doing there is comparing your assessment according to your scale with my assessment according to my scale. And
right, the thing to look out for here, he's got an equation x minus vt equals 0. So 0 at x prime there is 0. So it's 0 equals 0. Both sides of the equation are really 0. X prime equals 0. X minus vt equals 0. 0 equals 0. Worth making a note of because it can lead to the problems with the 0.
And so we get that x prime is equal to x minus vt. All we're doing there is comparing your assessment according to your scale with my assessment according to my scale. And of course, for the moment, we are going to assume that when we each measure time, we measure the same time. So the assumption that we're going to make is that the time that I measure, t, will be the same time that you measure, which is t prime.
Okay, so now he's saying that, and that means he's really trying to work within Newtonian physics. All this so far, he's trying to do it in Newtonian physics. Far as I'm concerned, he's not doing the maths very good. It's not. If this is not math, this is maths not being handled very well, and he's doing it within the context of Newtonian physics at the moment.
With my assessment according to my scale. And of course, for the moment, we are going to assume that when we each measure time, we measure the same time. So the assumption that we're going to make is that the time that I measure, t, will be the same time that you measure, which is t prime. That we are going to discover is actually not correct. But it's an obvious thing.
Right, he's going to say disprove Newtonian physics, and of course he's going to be wrong about that.
The assumption that we're going to make is that the time that I measure, t, will be the same time that you measure, which is t prime. That we are going to discover is actually not correct. But it's an obvious thing, so we'll assume it for the time being. And how can we make that happen? Well, what we can do is we can have a situation whereby as you, this is you, and this is me, as you pass me, travelling at v, we can have an arrangement whereby there can be a very short contact between our two boxes, which synchronises the watches or the clocks on both of our relative locations. And that means that at some time in the future, when you have reached here, I'm still here, you've reached here, we would say that if 5 seconds has passed on my watch, 5 seconds will also have passed on your watch. We can each, of course, also measure the speed of light in our respective frames. And I will say that the speed of light is the distance travelled divided by t, and you will say that the speed of light is x prime divided by t prime, because we are each measuring.
Right. He's using c is equal to x over t here, when earlier he was using x minus vt equals 0, so x equals vt. So he's being a bit loose in his notation here. It would be preferable if he sort of like used a x1 and a t1 there, and a x2 and a t2 here, and probably similar here. But he's just being very lax in the way he's doing his maths.
In our own frame of reference. But Michelson and Morley says that we will both get the same result.
Yeah,
so now let's take the formula.
He's quoting Michelson-Morley again, and of course I pointed out to you what he's saying about Michelson-Morley is incorrect.
And you will say that the speed of light is x prime divided by t prime, because we are each measuring in our own frame of reference. But Michelson and Morley says that we will both get the same result. So now let's just take the formulae that we've just derived and see what comes from them. Firstly, we established that x prime equals x minus vt. That was simply to compare you saying that you don't move in your frame of reference, and I say, but you do move in my frame of reference. We also established that c is x over...
Right. He's same equation as before, he's just writing it down again. And I'll remind you that he has x prime is equal to 0. So that there is 0.
Reference, and I say, but you do move in my frame of reference. We also established that c is x over t, which means that x equals ct, and we established that c is x prime over t prime, which means that x prime is ct prime.
So I disagree that this is established, but putting that aside now, we are dealing with the maths that he claims is coming out from the experiment, and so we just happen to accept that this is the maths he wants to use, and we're going to see what problems this math is going to lead him to. So just accepting it for the time being.
That c is x over t, which means that x equals ct, and we established that c is x prime over t prime, which means that x prime is ct prime. So let's feed these into this formula here. X prime is ct prime, so up here, x prime is ct prime equals x, well that's ct, minus vt, which means that ct prime is equal to t into c minus v. Now, if...
and I'll remind you, he's using that, so at the moment it's still 0 equals 0.
Minus vt, which means that ct prime is equal to t into c minus v. Now, if t prime equals t, which is what we think is the case, the clocks remain synchronized, then we have that c is equal to c minus v. That obviously cannot be true unless v is 0.
Right, so far all this has been Newtonian physics, and he's been plugging in the false assumption about the constancy of c, and he's derived from the maths that c equals c minus v, and that equation can only be true if v equals 0, because c is non-zero. So that is the consequences of that. But he's going to say, oh no, v is non-zero, so therefore that equation does not make sense. And so he's going to have to do some mathematical manipulation to get away from that.
Prime equals t, which is what we think is the case, the clocks remain synchronized, then we have that c is equal to c minus v. That obviously cannot be true unless v is 0. But v is not 0 because you are moving relative to me. So we've arrived at a nonsense. Something has gone wrong somewhere. What has gone wrong? Well, let's go back to our starting position again.
So what I'm pointing out has gone wrong is he's misinterpreted the Michelson-Morley experiment, but we are now working through from his misinterpretation of the Michelson-Morley experiment and doing the maths based on this misinterpretation. So putting aside the misinterpretation of the Michelson-Morley experiment, that would be a correct conclusion. That c equals c minus v, with v non-zero and c non-zero, then that is false. Then you would have to change the maths.
So we've arrived at a nonsense. Something has gone wrong somewhere.
Nonsense.
What has gone wrong? Well, let's go back to our starting position again, which is that x prime is equal to x minus vt. And if that's the case, I can simply reorganize that to say that x equals x prime plus vt. And since we're assuming that t prime equals t, I can put a prime on that so that both of these terms are measurements that you will make. So this is what measurement you make compared to the measurements I make. This is the measurement I make compared to the measurements you make. But something's gone wrong. So we are going to take these two terms and we're going to put an error term in them. Essentially, we're going to multiply both by an error term called gamma. We're going to say somewhere we've made a mistake.
Right. So without the gamma term, that is Newtonian physics equation. And he's claiming really that those equations don't work above. And now he's going to do a bogus thing. He's just going to multiply it by gamma and going to try to work out that it now works when you multiply it by gamma. So he's doing things really badly here. But we give him enough rope to hang himself.
So we are going to take these two terms and we're going to put an error term in them. Essentially we're going to multiply both by an error term called gamma. We're going to say somewhere we've made a mistake. So let's make that mistake equal to gamma and see if we can find out what gamma is. To work out what gamma is, what we're going to do is we're going to multiply both sides of these equations together. So we're going to have x prime times x is equal to this term times this term, which is x minus vt times gamma times x prime plus vt prime times gamma.
Right. I remind you what Matty's got. X prime is equal to 0. So x prime, that's 0 that side, and that side 0. So he's multiplying that times that. That is 0 times x. He's multiplying that times that, and that bit is 0. So that's 0 times all that. 0 times x, 0 times that. So if you paid attention to the mathematical fallacy on 0, division by 0, this is looking rather dangerous. This equation is looking rather dangerous.
And that's going to come out as x prime x equals, well, let's first take the two gammas. That's going to give you gamma squared into, now we've got to multiply these two terms in brackets. So x times x prime is x prime plus x vt prime minus vt x prime minus v squared t prime. All I've done is to multiply that bracketed term by that bracketed term. Now, it's all beginning to look a bit horrendous, but we remember that we determined that the speed of light was x over t, and the speed of light is x prime over t prime. It's constant, whoever's measuring it. And that means we can say that t is equal to x over c, and t prime is equal to x prime over c. Substitute these values for t and t prime into this formula here. What do we get? We get that x prime x is equal to gamma squared from here into x prime, well that's that, plus xv. Now instead of t prime I'm going to put x prime over c, minus v, and instead of t I'm going to put x over c times x prime, minus v squared, and instead of t prime I'm going to put x over c, x prime over c. So I've simply, in this formula, replaced all the t's and t primes by x over c or x prime over c respectively. Now again, that still looks awful, but you'll notice that x prime exists in every term. So I can divide throughout by x prime. If I divide this by x prime, I get 1 equal...
And that is 0. Reminding, he's got x prime is equal to 0. That is 0. X prime is 0, that's 0. That's 0. That's 0. And that's 0. He's got 0, and he's divided by 0, and he's got 1. He's just carrying on now. You're going to divide that by 0 and get 1 again. That's going to get the rest of these terms.
term. So I can divide throughout by x prime. If I divide this by x prime, I get 1 equals gamma squared, because that remains the same, into. This becomes 1 plus, if you divide that term by x prime, you get v over c. If you divide that term by x prime, you get minus v over c. And if you divide this term by x prime, you get minus v squared over c squared. And now you will see that these two terms cancel. And so we've now got that 1 is gamma squared into 1 minus v squared over c squared. Or, if you prefer, gamma squared is equal to 1 divided by 1 minus v squared over c squared. Or gamma is equal to 1 over the square root of 1 minus v squared over c squared. And that gamma is called the Lorentz transform.
And that is absolute nonsense. He's divided by 0, and if you paid attention to the beginning, that is absolute nonsense. He got this gamma factor and he derived it by absolute nonsense.
Over c squared. And that gamma is called the Lorentz transform. So what we're saying is that whereas we originally wrote that x prime equals x minus vt, which was simply comparing what you think in your frame of reference to what I think in my frame of reference, what we should have done is to multiply this term by gamma, which is the error term, and gamma is 1 over the square root of 1 minus v squared over c squared. So actually, that is what we should have had, and that's the relativistic correction. Now you'll notice something, that if the velocity is very, very, very much less than c, the speed of light, that v squared over c squared becomes effectively 0. And therefore you're just left with the square root of 1, which is 1, and that means that x prime equals x minus vt, which is what we thought was the case all along. It's only when v approaches or gets close to the value of the speed of light that this relativistic term comes into effect. So what we've shown is that special relativity, or the Lorentz transform term, has an effect as v gets very large. For ordinary speeds that we are used to, for example the train, it has no effect. That's why the ball rolling on the train, all you had to do was to add the speed of the ball to the speed of the train. But when you get...
Right. So he used x prime equals 0, ended up with this equation, and that is complete utter nonsense what the Matty's just done. And that doesn't stop him, he then carries on and does other nonsense as well. You just nonsense. He gets an equation and it's just nonsense. Right. So putting aside the lie on which Einstein's relativity is built, if you put that aside, ignore that it's built on a lie, the next step after that is to do mathematical nonsense. There we go. Back to there. The maths was slowly built up. There was a great deal in the maths that did not make much sense, but we concentrated on the bit where he decided to divide by 0. And that's when he committed the mathematical fallacy. So what we have is a division by 0. The maths is nonsense and is typical of what many relativity books have. Going back to Einstein does not help. he does such mathematical nonsense. I.e., if you look in Einstein's papers on relativity, his favourite trick is to divide by 0. So he's no help. He's just doing mathematical nonsense as well. Right, I want to point out the book Einstein's Mistakes. Where is it? Einstein's Mistakes. There. Right. This is a professor of relativity, and he's got a book out called Einstein's Mistakes: The Human Failings of Genius. Right. It says, although Einstein was the greatest genius of the 20th century, many of his groundbreaking discoveries were blighted by mistakes, ranging from serious areas of maths to bad misconceptions in physics and failures to grasp the subtleties of his own creations. Now, this book points out some of Einstein's maths mistakes, but doesn't point out all of them. And this person is committing the division by 0. Same sort of thing that Einstein does. Einstein commits serious mathematical mistakes. This book does not go far enough to point out how bad Einstein's maths is. So this person here, he's quite happy to use Einstein's bad maths. Whereas this professor who's written this book, he might be more aware of what's going on. He might not want to go by that bad maths, but anyway, that is what's being used. Right. There are people who do not realise the maths used is nonsense and believe Einstein's relativity. There are people, I missed out the word. There are people who do not realise the maths used as being nonsense and believe Einstein's relativity. While there are people who do recognise it as nonsense but still believe Einstein's relativity regardless. I think there are people going into physics and being subjected to this sort of nonsense in the maths and realising it is nonsense, and when they are faced with believers insisting on believing this nonsense, those people then give up on physics and go and do something else instead. I.e., this nonsense is acting as a block to people, sensible people coming into physics. In other words, those people who will be good at maths become discouraged with entering physics, and that leaves the people in physics as being those who are prepared to do mathematical nonsense. It's acting like a filter system. If you're good at maths and you go into physics, you think, what the F's going on here, and you get discouraged and you want to leave. Whereas people who are mathematically incompetent go into physics and it doesn't matter that they're mathematically incompetent. I.e., in the physics department, the lunatics have taken over. For those staying in physics as regards the maths, the philosophy seems to be, by these people, that they don't care that the maths is nonsense. And that is, if they recognise the maths is nonsense, because some of them don't recognise the maths is nonsense. Those that recognise that the maths is nonsense, they will insist something like the maths fits what has been observed from experiments. So they're going to insist on experiments confirming their mathematical nonsense. but the maths that they fit to experiments is nonsense. So all they're doing is giving a nonsensical mathematical interpretation of experiments. And I'm shouting that they are talking nonsense about experiments. It is the principle of GIGO, garbage in and garbage out. Their method is to apply mathematical garbage to experiments, and then garbage comes out as the results of these experiments. I.e., using nonsensical maths just means that their experiments become meaningless nonsense. Right, so these lunatics in the physics department will laugh. They will laugh at that. You point out to them they're talking nonsense and they will just laugh. Crazy laughter of lunatics. And they will say something like, physics is not maths. So they're prepared to accept nonsensical maths and say it's not, say math is not physics. Physics is not maths, they will say. So it doesn't matter that the maths is nonsense. If they mean by this that they don't use proper maths, then I would agree it is not proper maths that they are using. They're just using garbage. And that's my conclusion. All they're doing is using garbage. Garbage in, garbage out. Thank you. That's the end. We're back to the conclusion. Mathematical nonsense as used by Einstein's relativity. That's my conclusion. Thank you.